I have a simple question. What is 158 plus 763? Students learn how to solve this early on, but what if, hypothetically, we didn't know the method to solve it? And how can we find it? And what about the methods for subtraction, multiplication, or division? First, we should look at how our numbers are organized. Our numbers are organized from right to left in ones, tens, hundreds, and so on. And each digit tells us how many there are in each place. So in this case, there are 8 ones, 5 tens, and 100. We could also write an expanded form to get a better look at what's going on. So let's go back to the addition problem. If all numbers follow this system, then it would only make sense if the answer to this would be the sum of the ones columns, the tens columns, and the hundreds columns. So let's arrange it vertically so we could line up all the columns. And also let's just expand it so we kind of have a better look at what's actually happening. So first we'll add 8 and 3, which is 11, but 11 is too big for this ones column. So what we can do is split this 11 into 10 and 1, and then we'll just carry that 10 into the tens column. Alright, so now we could add up the tens column. 10, 50, and 60 is 120. So we run into the same problem. 120 is too big for the tens column. So we can just break that up into 120 and then carry the 100 into the hundreds column. Now let's add up the hundreds column. 100, 100, and 700 is 900. And there we go. We got our answer. Now let's condense this. Let's put the expanded form back into standard form. And now let's just compare it to the expanded method. On the right is the method that we learned in school, and on the left is, as you can see, the same method, but expanded. You can actually kind of see what's going on, and you get a better picture of how we carry. Now let's move on to subtraction. So we should organize it vertically again, because it should be the same. But obviously this time we're subtracting instead of adding. So let's expand it. And notice how I have the minus sign outside of parentheses. This is just to make sure that that minus sign goes to each number. So I'll just rewrite it like this. So now we'll do 1 minus 3. Now 1 is smaller than 3, and we can't have a negative number in the ones place. So what can we do? Well, how about the 1 just borrows 10 from the tens place and then just adds it to itself? That makes it 11. So now we can do 11 minus 3, which is 8. And now we have the ones column. Now we can move on to the tens column. 10 minus 60. 10 is smaller than 60, so we run into the same problem. So what if we borrow 100 from the hundreds place and then make the 10 110? Now we can do 110 minus 60, which is just 50. Now we can just subtract the hundreds column. 800 minus 700 is doable, so it's just 100. And there we go. So let's condense this again. So here's the method that we learned in school compared to the process we just went through. And again, it's the same process. It's just the way we did it was expanded. So we could see the regrouping or borrowing more accurately. Or on the right, it's just more of a shortcut, but it's kind of hard to understand what happens. So what about multiplication? Now this one we could think of geometrically, because think of a rectangle. To find its area, you multiply its length by its width. So why don't we turn this 25 times 5 into a rectangle with sides 25 and 5? So the area of the rectangle must be the same as 25 times 5. So how about we split it up into two easier rectangles, because it's the same area of the larger rectangle, but it's in easier bits. So if we add up the areas, we should get the area of the entire rectangle. So 5 times 5 is 25, and the second rectangle also has a side length of 5, so 5 times 20 is 100. So let's just combine these two rectangles back into the large one. And there we go. 25 times 5 is 125. Now let's just break this back up again. we can write this 20 plus 5 times 5 like this. And the reason why I'm showing you this rectangle is that it's a proof of the distributive property, where basically I could multiply 5 by 5 and 5 by 20. So, and the reason why we're doing this is to make a method that's more abstract. So we don't need to draw a rectangle every time we want to do a multiplication problem. So let's just expand this again, and then we can apply the distributive property to solve this. So we start with 5 times 5 is 25, but 25 is too big for the ones place. So we can just take that 20 and then carry it into the tens place. Alright, so now we can do 5 times 20, which is 100. But we have to remember that there's still a 20 there, so we should bring it down so we get the entire answer. Now let's do it again, but with the simplified process that we learned in school. 5 times 5 is 25. You carry the 2. And then you 5 times 2 is 10. But here's a trick. Since it's the last digit we're multiplying, instead of bringing down, carrying, and all that, we could just do 5 times 2 is 10, and then add the carry number, which is 2 in this case, and then just stick it on the end. Alright, so what if we have 2-digit numbers multiplying each other? Well, let's go back to the rectangle. Why don't we just add another row to represent this? So 20 plus 5 times 5 plus 10, which is the same as 25 times 15. And then we can just start the same way that we did last time. 5 times 5 is 25. Carry the 20. And then 5 times 20 is 100. And then carry the 20 down. So then what do we do next? Well, if we look at the rectangle, we could just multiply 10 by 5 and 10 by 20 to get the areas of the last two rectangles. So let's do that. Also, we should cross out the 20 because we already carried it down, so we don't want to confuse ourselves. So we'll do 10 times 5, which is 50. Remember that we have to keep all the numbers in the correct column, so make sure you write it in the tens column. So now we can do 10 times 20, which is 100. Or 200, sorry. So then, there we go. So then we have to notice that there's still an empty spot in the ones place. So since there's nothing there, we could just do a plus 0 just to keep everything, lined up. So now we could realize, what do we do with these two numbers? Well, realize that each of these numbers are just one of the rows of the rectangle. So we could just add them up to get the area of the entire rectangle, or also the answer to 25 times 15. And there we go. So let's look at the same process, but simplified. So as you can see, we get the 125 as normal. We cross out the carry 2, and see how that there's a 0 in the ones place. That's because what's really happening is when we multiply the 1 by 25, we're really multiplying 10 by 25 because it's in the tens place. So that's why everything gets shifted over left. If it were 100, it would shift over 2 spaces. So let's move on to division. So let's define division. Well, one way we could think of division, and we'll use 8 divided by 2 as a simple example, as repeated subtraction. How many times do I have to subtract the divisor, which in this case is 2, to get to 0? Well, we subtracted 2 4 times from 8 to get to 0, so 8 divided by 2 is 4. Now this will help us when we calculate something like 168 over 6. Now I'm going to rewrite the original problem like this because it'll help us later on. So let's draw another rectangle, but this time we have the area of the rectangle and we have one side of it. So now we need to find the length of the other side, and that will be our answer. So let's just split it up into easier rectangles first. We do this because we want to have nice place value numbers to add up in the end. So how many times can 6 go into 160? Well, I know it can go in at least 20 times, but it could obviously go in more because 6 times 20 is only 120. But we'll just put it greater than 20 for now. So how about we redraw the rectangles again just to solve for one part of the length because we know it's at least 20. And we'll write 20 up there so we'll keep like a running total. So now we have this part to solve. We already have 20. We need to solve the rest of the length of that side. So let's just ignore this side for now. And we'll also subtract it because we're trying to get to 0. So we'll subtract it from 168. So then we'll see what's remaining. So we have 48 remaining. So how about we combine the 40 and the 8 into 48. So now we have a rectangle with an area of 48 and side 6. So the side of this rectangle must be 8 because 6 times 8 is 48. So now we have the entire length of the rectangle. So 168 divided by 6 is 28, but let's continue with the process to keep it consistent. So we write the 8 at the top, and then we multiply the 6 and the 8, and we subtract it to get to 0. So technically we're done now. So now we can just combine the 20 and the 8 to get 28, and then that's our answer. Now let's look at the simplified process. This is how we learn in school. 16 divided by 6 goes in twice. So 6 and 2 is 12. And then you could subtract that, and that's 4, and you carry down the 8. Now 48 divided by 6 is 8. So you multiply that back out, and then we have 0, so we reach the end. So as you can see, it's the same process, but obviously it's not as clear of what's going on in our simplified method as it is with our expanded method. Like when we're subtracting 12 from 16, we're really subtracting 120 from 168. And that's why we bring down the 8 to carry the rest of it. So why go through the pain of expanding these methods when we know there are simpler ones? A lot of times in math we're given formulas or methods to solve problems, but we aren't really taught where they come from. And that can be frustrating. Like take long division, for example. You divide, you multiply, you subtract, and bring down. It just seems very arbitrary. But when you learn the logic behind it and where it came from, you can see that it is actually intuitive. And it's kind of cool that we have a shortcut because we took this lower level idea and we basically just skipped some of the work to make it easier for us. And I think that's beautiful. Thank you.